Welcome. This is Michael. I am the creator of Differential Geometric Algebra compute using Grassmann.jl and Cartan.jl. And this is a new research paper that I've been working on. And yeah, so we're just gonna take a look at it right now on this video here, and that's the Grassmann.jl logo with the Julia language and the exterior algebra in the logo combined. And yes, so this is the abstract. Take a look at this. Initially, Grassmann.jl and Cartan.jl introduced the DirectSum formalism into computational language design for differential geometric algebra, thus enabling the construction of custom algebras through metaprogramming. Grassmann.jl pioneered a novel type system design along with its syntax and semantics, which has undergone significant refinement through many years of development and continuous improvement. Cartan.jl represents a groundbreaking extension of capabilities offered by Grassmann.jl, marking a pioneering, fully realized implementation of numerical differential geometric algebra based on TensorField representations over a FrameBundle and the immersed topology of the FiberBundle. Grassmann.jl and Cartan.jl build on Julia multiple dispatch and metaprogramming capabilities, presenting a new computational language design approach to interfacing with differential geometric algebra based on a new sector integral theorem. This pioneering design not only actualizes but also elevates computational language syntax to new heights using the foundations of Grassmann.jl and Cartan.jl. The Grassmann.jl and Cartan.jl packages introduce pioneering computational language designs, having inspired imitation projects and thereby validating the project's relevance as significant advance in computational mathematics. So the packages Grassmann.jl and Cartan.jl can be used as a universal language for finite element methods based on a discrete manifold bundle. Tools built on these foundations enable computations based on multilinear algebra and spin groups using the geometric algebra known as Grassmann algebra or Clifford algebra. This foundation is built on a DirectSum parametric type system for tangent bundles and vector spaces, generating the algorithms for local tangent algebras in a global context. Geometric algebra mathematical foundations for differential geometry can be used to simplify the Maxwell equations to a single wave equation due to the geometric product. With this unifying mathematical foundation, it is possible to improve efficiency of multidisciplinary research using the geometric tensor calculus by relying on universal mathematical principles. Tools built on this differential geometric algebra provide an excellent language for the newly presented sector integral theorem, and also the Helmholtz decomposition and the Hodge and de Rham cohomology, for example. The Grassmann.jl package provides tools for computations based on multilinear algebra and spin groups using the extended geometric algebra known as the Grassmann, Clifford, and Hodge algebra. And the algebra operations include exterior, regressive, inner, and geometric, along with the Hodge star and boundary operators. Code generation enables concise usage of the algebra syntax. DirectSum.jl multivector parametric type polymorphism is based on tangent vector spaces and conformal projective geometry. Additionally, the universal interoperability between different subalgebras is enabled by AbstractTensors.jl, on which the type system is built. The design is based on Tensor Algebra V, abstract type interoperability from AbstractTensors.jl, with a k-module type parameter V from DirectSum.jl. Abstract vector space type operations happen at compile time, resulting in a differential geometric algebra of multi-vector forms. Building on the Grassmann.jl foundation, the Cartan.jl extension then defines TensorField as a subtype of global fiber for both a local product space and general immersed topology specifications on any FrameBundle expressed with Grassmann.jl algebra. Many of these modular methods can work on input meshes or product topologies of any dimension, although there are some methods which are specialized. Cartan provides an algebra for FiberBundle sections and any associated bundles on a manifold in terms of Grassmann elements. Calculus of variation fields can also be generated with the combined topology of a fiber product bundle. Furthermore, the fiber product enables construction of homotopy bundle types. The Cartan package standardizes composition of various methods and functors applied to specialized categories transformed in terms of a unified representation over a product topology, especially having fibers of the Grassmann algebra and using Cartan methods over a FrameBundle. So let's review the DirectSum parametric type polymorphism one more time. Definition. Vector space is a field's k-module. So let V be a k-module, abelian group with a plus operation, with an element 1 in k such that 1 times V equals V by scalar multiplication. So that means that there's a scalar operation built in, like this, over the field K, satisfying these distributive law and over the vector addition and the field addition, and then the associative compatibility. In the software package Grassmann, a generating vector space K module is specified as a value as some kind of a subtype of TensorBundle, which is then repackaged as a submanifold and then put as a parametric, as a parameter in the tensor algebra type system. The abstract tensors package is intended for universal interoperation of the abstract tensor algebra type system. All tensor algebra V subtypes have type parameter V, used to store a submanifold M value, which is parameterized by M, the TensorBundle choice. This means that different tensor types can have a commonly shared underlying k-module parametric type expressed by defining V submanifold M. Each tensor algebra subtype must be accompanied by a corresponding TensorBundle parameter, which is a fully static at compile time. Due to the parametric type system for the k-module types, the compiler can fully pre-allocate and often cache. Additionally, a universal unit volume element can be specified in terms of linear algebra.uniform scaling, which is independent of V and has its interpretation only instantiated by context of the tensor algebra V elements being operated on. Interoperability of linear algebra.uniform scaling as a pseudoscalar element, which takes the TensorBundle form of any other tensor algebra element, is handled globally. This enables the usage of I from linear algebra as a universal pseudoscalar element defined at every point x of a manifold, which is mathematically denoted by I or I of x and specified by the g of x bilinear tensor field of the tangent bundle on M. utility methods such as scalar. So there's various utility methods defined. Now let's focus on the next definition of linear dependence. Let V be a vector field over a field K. Then the set Vi of I is linearly dependent if and only if the sum from I equals 1 to n of Ki Vi equals 0 for some non-zero K values, for some non-zero vector K basically, or element K basically. And if that's the case, then they're linearly dependent if it's equal to 0. That's just a definition of linear dependence that it's very standard. And if we have linearly dependent set like this, then the exterior product of those is also 0. So this is now where we change to a different perspective. First, we had linear dependence in terms of this definition as this sum. Now we have linear dependence in terms of this exterior product being equal to 0. Initially, it is sufficient to understand that basically this is an operation which is equal to 0 for linearly dependent arguments. So when it's linearly dependent and it's equal to 0, that's a very important piece of information to start out with. However, then it becomes important to understand that this is an idea that comes from extending the Grassmann's product Vi wedge Vj equals negative Vj wedge Vi. And that actually implies that Vi wedge Vi equals 0, because it also equals negative Vi wedge Vi. And for those to be equal, has to equal 0, of course. And this is how we get linear dependence by extending the Grassmann product, this wedge product here. All right. So that's the annihilation of exterior algebra and the linear dependence. So we can talk about the dimension n submanifold. So in the nth exterior algebra space of V. All right. So note that writing the exterior product V1, V2, Vn not equal to 0 implies that this is a linearly independent set. And that means that this is isomorphic to a n submanifold. Furthermore, this n submanifold forms a one-dimensional basis subspace that is induced by this n submanifold. All right. So a scalar is just a 0 submanifold. This is just kind of, the 0 exterior algebra space, the scalars, is a vector space, or, the exterior algebra space of just a one-dimensional vector space K itself. And then the nth exterior algebra space is a vector space. And we have this property that the first exterior algebra space of the nth exterior algebra space is the nth exterior algebra space. and also the 0th exterior algebra space of the nth, you know, is the 0th of the V. So anyway, it's like these little properties you can explore. Then we talk about a way to define what the direct sum is. And here we can consider a set of linearly independent spaces. And then we have a bunch of projections with these subspaces Vi. And if we can construct this as a non-zero exterior product, then that's a direct sum. So that's one way to think about defining direct sums, but it's not so important for the computer implementation. It's just to introduce direct sums in the discussion. So now we have the grade M projection. So this is a way to talk about the exterior algebra space as its direct sum decomposition. So this is why we need to talk about introduce direct sums in the first place. So we have that the entire exterior algebra space is a direct sum of these grade projections from m equals 0 to n. And so it's the 0 exterior algebra space, the 1, and so on up to the nth. So it's the sum of all, the direct sum of all of those is the entire thing, basically. That's the point. And that's called a multi-vector space, basically. And we know what the dimension is, of course. It's based on the binomial expansion. And so the dimension of the whole thing is 2 to the n, of course. So we can look at the combinatorics of the power set. It's just something to illustrate an example, just to show we have this basis and we can have a power set of them. So we can have, you know, different subsets of these, of the whole set of them, you know. And so if we now apply the exterior product between these, because they're linearly independent, we can form this basis space so that they you can now apply the grade projection direct sum principle to these sub direct sums. So now this grade 2 space is a direct sum of these submanifolds, these products, and then it's part of the whole sum of the entire thing. And this is like a direct sum. So now let's talk about the M. So this is just kind of some notational stuff. So how do we define what the K module that we're working on of rank n? And we can have this kind of tuple of information that I've implemented, n, p, g, nu, and mu. And this is just to specify the presence of this conformal geometric algebra basis, which is a special case. So it's just kind of has its own special encoding that you can introduce if you want, and so this just signifies the ability to introduce this special encoding. And then we have G, which is the bilinear form, which is a metric tensor specification. And then the type of the tensor bundle NPG new mu encodes this information as byte encoded data available at pre-compilation, and mu is an integer specifying the order of the tangent bundle, which is the multiplicity limit of the Leibniz-Taylor monomials, and nu is the number of tangent variables, and n is, you know, the dimension of the thing. So and then this is what tells us how to generate, you know, how many, you know, basis vectors there are and things like that, and whether they have the conformal geometric algebra basis in them or not, and what the dimension of the space is, and so on. There's also optionally, you know, vectors and covectors and differential operators and scalar functions that can be encoded into this tensor bundle, but it's mainly the vector space basis is what's of interest for most of what we're talking about. So the rest of the functionality is just kind of interesting extra features that you can build in, but it's not that important. And the purpose of the tensor bundle type is to specify the k-module basis at compile time. When assigned in the workspace, V equals submanifold of a tensor bundle is typically used. So the metric signature of the submanifold elements of a vector space can be specified with this V command by using plus or minus to specify whether the submanifold of the corresponding index squares to +1 or -1. For example, S+++ constructs a positive definite three-dimensional tensor bundle. So constructors such as S and D are convenient. It is possible to change the diagonal scaling with D. So S is for signature basically, and D is for diagonal. So 1, 1, 1, 0 makes a diagonal metric with a 0 in it. Although the signature format has a more compact representation if limited to plus and minus 1. It is also possible to change the diagonal scaling 0.3, 2.4, 1. Fully general metric tensor is a type with non-diagonal components requires a matrix. For example, metric tensor of this matrix 1, 2, 3, 4, that's an example. Declaring an additional point at infinity is done by specifying it in the string constructor with the infinity symbol at the first index. For example, the Riemann sphere has this S+++, but with an infinity prefix. The hyperbolic geometry can be declared with this empty set symbol. So, for example, S empty set +++. And then the null basis from the conformal geometric algebra uses both of them combined, infinity and empty set. And these two declared basis elements are interpreted in the type system. Then there's a tangent map which can be used to specify mu and nu, but that's not necessary to know about for this rest of the paper. To assign V equals submanifold of a tensor bundle along with associated basis elements of the DirectSum basis to the local Julia session workspace it is typical to use submanifold elements created by the @basis macro. So using Grassmann @basis s minus plus plus, or you could use the basis minus plus plus like that notation. You know, there's different notations for it. So that invokes the Grassmann package, and it invokes this particular basis with this metric signature. The macro @basis v declares a local basis in Julia. As a result of this macro, all submanifold VG elements generated with M TensorBundle become available in the local workspace with the specified naming arguments. The first argument provides signature specification. The second argument is the variable name for V, the K module. And the third and fourth arguments are the prefixes of the submanifold vector names and covector names. Default is V assigned submanifold M, and V is prefix for the submanifold of V. It is entirely possible to assign multiple different bases having different signatures without any problems. The @basis macro arguments are used to assign the vector space name to V and the basis element to Vi, but other assigned names can be chosen so that their local names don't interfere. If it is undesirable to assign these variables to a local workspace, the versatile constructs of DirectSum.basis of V can be used to contain or access them, which is exported to the user as the method DirectSum.basis of V. Here's an example of DirectSum.basis of V, and that returns a DirectSum.basis object of V basically. So V, when you call V with integer arguments, that provides a convenient way to define a submanifold by using integer indices to reference specific direct sums within the ambient space of V. So at this point, let me get into an example in the session here. Oops. So let's do using Grassmann. And now let's do what was the example? S minus plus plus. All right, so we've got a basis here, or we can just make a three-dimensional basis like this, just any regular one. And then we have V as a submanifold object here. And now when you call it with indices, for example, 1, 3, this produces a new submanifold of that. And you could now create a new geometric algebra that's two-dimensional, which just has index 1 and 3 in it. Like this is now a two-dimensional geometric algebra, but it understands that it's a sub-algebra of the original three-dimensional algebra. Like you see, this is V13. That's the that's a multi-vector, that's an element in the multi-vector space where we omitted one of the indices, basically. So this is kind of like it's kind of a cool hidden feature that a lot of people may not know about, that Grassmann.jl has provided since the very beginning, pretty much. It has the ability to have these different subalgebras recognized, and one of the ways of dealing with it is using these indices. So this is these are the different subalgebras that you can make. And that's the that's the space, that's the parameter space, that's the parametric, that's the type that we put in, that's the object we put in the type parameter to parameterize the geometric algebra algorithms, which get automatically generated as you use geometric algebra using this programming language. So that's a little bit about generating basis elements. So the Grassmann's exterior product is an anti-symmetric tensor product. So let's try it out. So let's go back to basis 3. All right, so V1. So I made a video previously about getting started with Grassmann.jl, where I explained, that in the Julia REPL, the way you get, for example, the wedge symbol is you type \wedge, and then when you press the tab key, it produces that symbol. So, you could make a vector like this, v1 plus v2, and then you can take the wedge product, and the result will be 0, because that's a linearly dependent result, basically. So that's the calculation. And now if we make it different, now we get a different kind of result. So that's the Grassmann exterior product. So let's swap the order of that. Let's put v3 on this side, and now we'll see that this is the negative of the other one. And that's just what we're saying when we say that when you take these two vectors of one and take the exterior product, and you swap the order of the product, then it equals the negative of that. And if you have the same linearly dependent vector, then it equals 0. And so this generalizes to the multilinearly determinant transposition property. That's when you have like more, it's not just basis vectors like vi and vj, but you have more of them. And that's -1 to the m times n. And we can rewrite this if we scrunch the term on this side into omega and eta, then we compact the notation. Like we say omega is an element in the m exterior algebra space, and eta is an element in the nth exterior algebra space. So that makes for a smaller formula, basically, than this big long formula, right? Observe that the anti-symmetry property implies that the tensor product equals 0, while the symmetric property neither implies nor denies such a property. That's just a little remark for people who want to exercise their brain a little bit. Case of third order tangent bundle operators composition. So this is just another example that the composition of these partial differential operators forms another, direct sum space like this. And because, these are symmetric differential operators, you can just think of this as being it's linearly dependent with the swapped index, right? So in order to shorten the notation, the operation symbol is left out. So what we often do is we just put v sub 1 and then v sub 2 and then v sub 3 and then v sub 1 2 or 1 3 or 2 3 or 1 2 3. That's to shorten the notation, because we don't want to write out all these things every single time necessarily. So sometimes you just put it like that. All right. So the canonical choice of orientation is with the indices in sorted order, so that, for example, the antisymmetry is applied to rewrite v sub 2 1 into negative v sub 1 2. Or the property, well, for differential operators is that they stay the same, because that's the rule. In general, permutations of the indices get rendered as orientations of -1 to the k of a basis k module. So, it's just saying that, like, if you write, for example, 2 1, it'll reorient it like that, right? So, like, if 2 3 1 or 2 2 1 3, it'll just reorient it into the sorted order. It's just to keep a canonical choice of orientation. We don't want to make things too complicated for ourselves. So, so what are some of the permutations that we can deal with? So we have this definition, which you don't necessarily need to really memorize. This is just to demonstrate that it comes from somewhere. And basically, we have this reverse and grade involution operation and the composition of the two. And we basically say that these operations form a group. So sigma 1, sigma 2, sigma 1, 2, and then the identity operation. It's a set of automorphisms, which is a grade involution and the reverse operation. And the reverse is an anti-automorphism. And what does this mean? Well, it has this property, sigma 2 of vi wedge vj equals sigma 2 of vj wedge sigma 2 of vi. So these are the operations we have. So it's a little bit abstract, but if you know about geometric algebra, you'll already be familiar with what these operations are supposed to be. So these are the reverse operation is like what would happen if you were to reverse the indices. Like when what we did here is when we did 2, 1, it would be negative. And what if we take, you know, we asked what would the reverse of 1, 2 be? Well, that would be negative v 1, 2. So it just does that. So it just gives us that as an operation, as like a function that we can plug something into it, you know what I mean? And there's the other one is called involute for grade involution. And then we have the Clifford. That's the composition of the two, basically, you know. So we have these different operations that you can apply. People who know about geometric algebra will be familiar with the importance of these, and they'll be showing up later on. So we'll just keep it going. Now there's the real and the imaginary components of the exterior algebra space. And we can think of that as the sum or the averaging of basically an omega with its reverse, or omega minus its reverse, and then dividing it by 2 basically. And that gives us the real and the imaginary component. And if we do the same thing with a grade involution operation, that gives us the even and the odd components. And so this gives us this Z2 grading way to split it up into these 2 components, you know, the exterior algebra space. And in general, this can be extended to any Z2 grading projections. Grassmann.jl is a foundation which has been built up from a minimal K-module algebra kernel, on which an entirely custom algebra specification is designed and built from scratch on the base Julia language. Tensor algebra VK, where V submanifold M for a generating K module specified by M TensorBundle choice. So in this definition, we're going to get into what is the type system in Grassmann.jl, and what are the different types and what are the subtypes, and like what is the big picture here, basically. It's the big picture of the types that are implemented in Grassmann.jl. So TensorBundle specifies generators of the DirectSum.basis algebra, and all these are TensorBundle subtypes except for int. So int is just a base type in Julia, which in many cases can be substituted in place of a TensorBundle when you just want to induce a Euclidean metric of counted dimension. So it's an integer, right? So if the integer is 3, it could induce a Euclidean metric of, 3 dimensions being counted, right? That's what an integer could do, like that. So that's why we list integer here. But we more generally want something like a signature, right? So what if we have this plus and minus to specify the metric signature? An integer is not sufficient, so we have a signature TensorBundle type. Furthermore, we have a diagonal form TensorBundle type for defining any diagonal metric. And then we have the metric TensorBundle type, which can accept a non-diagonal metric tensor array. So that covers us basically for the fully general case of geometric algebra, that if we want to induce a Euclidean metric or a signature metric signature or a diagonal metric or a non-diagonal metric. The versatility of the Grassmann.jl TensorBundle type system is that it allows, has the expressibility for all those things. And then we have tensor graded VGK, which is a grade G element of the G exterior algebra space of V. So what does this include? Well, this could include the chain VGK. So this is like an abstract type. So this includes other subtypes. So the chain VGK is basically what many other people call like a K vector or a grade G vector or whatever, but it just means in homology and cohomology theory, we have these things called chain complexes, and so it's appropriate to use chain here because these elements are technically also chain complex types. And so chain is a nice short word that can be typed quickly in the programming language. And technically in pure mathematics, these are part of the chain complex. So, but these are G vectors, basically. These are from the grade G. So it has the complete basis for the grade G space with the K module. Then simplex is an alias for the column module of a chain. So basically think of having like a chain which has, more chains as its K module algebra type, so that it's basically columns of a matrix basically, and that forms the simplex. Then we have tensor term VGK, which is a subtype of tensor graded VGK, but it's just a single coefficient. So while these form a complete basis, the chain, this is just kind of a single coefficient thing. So we call them tensor term because it's kind of like it stops there in terms of tensor algebra. Like it doesn't factorize into like more basis coefficients. So it's just a single basis coefficient, right? So tensor term, because it terminates, it's terminal in terms of like the abstract syntax tree of coefficients. And so 0 is a zero value which preserves V in its algebra type. So we have 0 of V with, it's a parametric type which parameterizes V while it simultaneously expresses that the value of the tensor is 0 while preserving the parameterization of the underlying TensorBundle choice. So the submanifold VGB is basically if Vi through Vij G are the basically the basis vectors, and we have G of them. That's a G submanifold with sorted indices B. So like we said before, they have sorted indices, but if it's like 5 V1 2, then it becomes a single. So a submanifold is just V1 2. This is a submanifold, right? While 1 V1 2 is a single. So there's a difference between just V1 2 and 1 V1 2, because this is just a submanifold, which is kind of like an abstract thing single actually has a coefficient value associated to it. So like you know, like this int. So submanifold doesn't have an int associated to it. So that's what a single is. Single has a submanifold paired to like a coefficient, basically. So then we have abstract spinner. So these are subtypes of special subalgebras of the exterior algebra space. So then one of the first ones is the couple. This is a new thing, a new concept I introduced into geometric algebra, like computer algebra implementations, which I came up with in Grassmann.jl. And this is what I call a couple. And a couple is basically the sum of a scalar and any other single. So which means that it basically combines a submanifold and a scalar value, and that's what I call a couple. And it kind of generalizes just like what a complex number would be, but it could be a hyperbolic number or a complex number or whatever, you know. So it's a more general kind of thing than, you know, like in Julia we have this 1 plus im. It's a complex number type, right? Oops, I have an extra parentheses there. All right, so 1 plus v1 2 in Grassmann.jl is a couple. Now it says Gaussian integer right there, but Gaussian integer is just, you know, another way of saying couple. But it's with integers basically, so Gaussian integer. So if you know what a Gaussian integer is, then you'll know what that is, but it's just another alias. But like if we do 0.1 plus v1 2 and we dump that, then we can see that it's just a couple, right? Couple has two values. Then we have something called a pseudo couple, and that is the complement of a couple. So if you have couples like 0.1, you have singles and you have couples, right? And then you take the sum of two singles and get a couple. Now what if we want to take the complement of that? That's a pseudo couple. So a pseudo couple is when you have a pseudo scalar plus a single, and that's a pseudo couple. So with the introduction of the couples, I had to introduce the pseudo couples as well. And so but pseudo couples are not the same as couples. They don't have all the same kind of properties as couples. They don't behave the same way at all. Pseudo couples are quite different in a lot of ways, but they're complementary to couples. So you can't just have, you know, couple and then somehow have it pseudo couples be the same thing. No, pseudo couples are something fundamentally different from couples, but in a lot of ways they're similar in that they're both, you know, complementary to each other. But these are couple and pseudo couple, so these are important abstract spinner subtypes that exist in Grassmann.jl, and they're built into so many different functions and stuff. They automatically output. They Grassmann.jl can be optimized, you know, when it detects that there's a couple or a pseudo couple, and it's a very nice inclusion in the type system, and it can optimize a lot of algorithms to have the expressibility of it. And this is something new that was invented basically in Grassmann.jl, including this entire type system is basically something new, but this specifically is entirely new. Like I'm not aware of any other geometric algebra implementations which would have had something like a couple and a complementary pseudo couple implementation. And then we have spinner and co-spinner, like in its fully general sense. What I'm talking about here, like complex numbers exist, in the base Julia language, so that's nothing special. But I'm talking about the fully general approach, that how this all fits together. So spinner and co-spinner. So that's the even and the odd graded terms. That just completes the whole thing. So basically, for a lot of operations, it's convenient to be able to just specifically talk about the even and the odd graded spaces. And so that's why we have spinner and co-spinner as a specific subtype of abstract spinner. And then we have the fully general multi-vector space, which is just the complete, basis for the exterior algebra with the K module. So if we proceed further, what do we have here? We have tensor nested subtypes are linear transformations. Tensor operator VWT, linear map VW with T data type. So what this basically means is we have tensor nested, and then there are subtypes of that, which are linear transformations typically. Not necessarily, but typically it's just for the sake of most situations, that's why it's written like that. But and then a specific one is a tensor operator, and that's a linear map from basically V to W using some kind of data type T. And that's a tensor operator. So it's a very versatile type, because it can have different data types and different vector spaces V and W. So it's a versatile way of expressing linear maps. And then endomorphism is when it's V on V. It's a tensor operator, which is also an automorphism. And then we have diagonal operator. That's a diagonal map. So we have diagonal morphism and diagonal outer morphism, and these are just aliases of diagonal operators. So we only need one type, which is diagonal operator, and then we can just add more aliases of it to increase the expressibility of our type system. And then for outer morphism, that extends a endomorphism to its full exterior algebra space. So basically, if you have like this endomorphism F, and you apply F to V1, and then take the exterior product with F applied to Vn, that should equal F applied to the exterior product of V1 through Vn. And that's called the outer morphism property. And the way, if F is, this can be represented using a tensor operator, or a tensor representation of that. And so the outer morphism basically is a way of giving a representation to that more explicitly, basically. So then we have the projector type, and that's a linear map where f of f equals f is defined. And the way it works is basically the dyadic tensor product of x divided by the absolute value of x with itself. And the dyadic outer product of the matrix algebra, and that forms a projector element of a linear map. And that's like a specific type. And then another more general type is a dyadic tensor type, and that's a linear map from V with types x and y. And basically that forms a outer product like this, but it's not, it's just x and y. It's like not restricted to being like a projector linear map, but it's just the fully general, basically dyadic tensor map. All right, so this is what gives us a lot of versatility in terms of having the geometric algebra, tensor algebra basis, like the graded algebra elements, the single coefficients, the coupled coefficients, the spinners and co-spinners and abstract spinners and the multivectors. And then we have basically the linear maps, mostly like the tensor operators and the endomorphisms and diagonal operators and outer morphisms, projectors and dyadic tensor products. So the Grassmann.jl was the first to define the comprehensive tensor algebra of V type system from scratch around the idea of the V submanifold value to express algebra subtypes for a specified K-module structure. So basically, this is a new comprehensive type system that was built from scratch around these different concepts, and it shows what's available here. So let's just keep it moving. Accessing a metric tensor V produces a linear map G, which can be extended to an outer morphism. So let's just take a look at that as an example. Like, let's just do the metric tensor, right? And now let's do outer morphism of that. Now this is just an identity, right? Because it was Euclidean metric. But we can see some of the things that we were just discussing in action. So this is an endomorphism with a simplex data type. And then we have a outer morphism which contains the same simplex and then extends it with the additional terms for the exterior algebra space, the full one. All right, so that's an outer morphism. And the way, so metric tensor gives you that. Metric X tensor gives you the outer morphism. So many cases it's useful to reference the full outer morphism instead of just the metric tensor as like, you know, this 3x3 matrix. Sometimes you want the full outer morphism, right? So that's why the syntax, the API gives you the option between these two, and the difference is like this one's called metric tensor and this one's called metric X tensor. And that's just what this is saying here, that accessing the metric tensor produces the linear map, which can be extended to the outer morphism given by the metric X tensor. And then to apply the metric X tensor to any Grassmann element of lambda V, the function metric can be used on the element. So for example, we have V1, 2, right? And we can apply the metric to it. So metric of that just means that it applies the metric tensor. Like if you take the metric X tensor and then apply V1, 2 to it, apply it to V1, 2, I mean. Another notation for that is metric of V1, 2. And you'll notice that the advantage is, you know, like if we do this, because this outer morphism, the way it's represented, the result of this operation ends up producing a chain instead of a single. Whereas if we use this operation metric of V1, 2, it preserves the type of it. You know, like this was a single on its input, but on the output it was a chain. But here, when you plug V1, 2 into metric, it applies the metric extensor, but it preserves that it's a the type that it was a single, basically, right? So like these values are 0, right? And that those could be discarded But when you express the operation in this way, like by applying the metric tensor as an outer morphism to v12, this is too cumbersome of an operation, right? So that's not the most efficient way to do that operation, right? You can if you want, you can do it like this. You can ask for the metric extensor and then plug and then apply it to v12, right? But that's not the most efficient operation. The most efficient operation is this metric of v12, and it preserves that it's a single, right? Or if you have 1 plus v12, it preserves that it's a couple, right? But that was just for co-metric. Anyway, so Grassmann.jl and the Hodge complement. John Brown has discussed the Grassmann duality principle, stating that every theorem involving either of the exterior and regressive products can be translated into its dual theorem by replacing the exterior and the regressive product operations and applying the Grassmann complements. So the Grassmann complement, expressed as unary operator, which is sometimes called the right-hand rule in physics, is derived from John Brown's common factor theorem. Given a pseudoscalar b1 through n in the nth exterior algebra space, the linear map for the mth exterior algebra space element to the n minus mth exterior algebra element is the following. So this is just a way to express it. So minus 1 to the m times m plus 1 over 2 plus the sum from j equals 1 to m of I sub j. And then the exterior product where k is not equal to ij of v sub k. And then it's the grade n minus m projection of that, basically. So that's denoted the complement right operation because it's the right-hand rule. While the linear inverse, so in Julia we use the exclamation mark operator. While the linear inverse of exclamation mark is a similar map complement left expressible by reorientation. So if we're given a similar input, then minus 1 time to the m times n minus 1 times the complement right of the input element is then the grade m of the grade m projection input element, then produces the complement left output. Together these form an orthocomplementary propositional lattice, which can be, expressed using something like De Morgan's laws, where the regressive product satisfies the Grassmann laws with the Grassmann complement and the exterior product. So what you can do is we have our three-dimensional basis. So the complement of V1 So we have complement left and complement right. We have these different operations, and they just basically reorient the result and change us to an n minus m space. Then we have the Hodge complement, which is expressed as unary operator star, and we define it as the composition of complement right and the metric as a linear operator. So star equals the complement right composed with the metric. as an outer morphism. This linear operator is also called complement right Hodge, or only Hodge. So now we have Hodge, or complement right Hodge. Complement right Hodge, or star. So here Hodge for Euclidean metric, it's not going to make much difference from using the exclamation mark, because it's the metric was the identity metric. The original Grassmann complement is equivalent to the Hodge complement with the Euclidean metric tensor, making metric an identity. So like I just said, when the metric is an identity, then the difference between this Hodge complement and the right-hand rule, there's no difference between them. The interior contraction is the regressive product of eta and star omega. Is defined in terms of the regressive product and the Hodge complement. By default, the right contraction is used, which I denote here with a greater than symbol. But there's also a left contraction with the swapped arguments. And then in some other literature, there's different kinds of contraction conventions. And that convention is accessible here as well, and with a double symbol instead of using a single symbol. If you do a double symbol, then that's the alternative convention where the reverse is applied on the input, and by applying that, it results in their convention. And then so that's the interior product. So an example is, the inner product of something like this, or like the inner product of two vectors. Right, so that's a vector, and then take the inner product of those, right? Another way to get that result is like this, right? So that's the definition, right? The regressive product with the complement. So, and because it's a Euclidean metric, we don't need to use the Hodge complement. So you could take an inner product like this if you want, but there's an actual inner product operation built in. Using coupled subspaces in the block matrix structure of metric tensors, a basis element can be factorized in a corresponding way. In particular, for the diagonal metric, this is simply the basis factorization. However, a non-diagonal metric induces a more complex block factorization. So this leads us to the definition of the Clifford geometric product. So if AI is an indecomposable basis element with regards to the block matrix structure of the metric tensor, and B is a grade K exterior algebra element space, graded element, then define the operation O minus as either AI O minus B equals AI wedge B plus AI contract reverse B, or B O minus AI equals B wedge AI plus reverse of B contract AI. Now we're gonna stick with this case, so there's like these two cases, right? And for the rest of the definition, we're just going to stick to the first case. If A is like A1 wedge up to am are a basis factorization, then the geometric product of a1 to am is equal to the exterior product a1 to am, because we're able to form a basis factorization of those. Furthermore, if a1, if the geometric product of all these can be, the geometric product of capital A times B can be expanded. So we're going to take this exterior product, this geometric product, A times B, and it can be expanded in such a way that refers to A sub m times B, right? And then we can apply this rule. And then we can take the result of that and use A sub I and apply it again, right? So it's like a recursion rule, right? So we can recursively apply it. And it can be expanded to distribute the operation of A times B. So that's for the fully general way with respect to the block matrix structure for the factorization of the basis elements. All right? And by applying this principle with the distributive law over the entire exterior algebra basis, the Clifford product is defined. And in Julia, the multiplication symbols, like the regular star symbol, can be used for geometric products, right? So v12 times v1, right? So like 1 plus v12 times, 1, 2 plus, 3 v12. That is like complex multiplication, like complex number multiplication, right? Because the result is still a couple. Let's make that like a... So like you see, it still is a couple, but if we change the indices, now it's a spinner. Or a quaternion, right? So now it's a quaternion. Quaternion is actually... Oh, I forgot to... did I mention it in the paper? I don't know. But quaternion is like another alias for spinner, right? So... yeah, so quaternion is this that's with the geometric product. Oh, here we go. So like if you do the multiplication like this, then it remains a couple, but if you do the multiplication like this, these two couples multiplied become a quaternion, right? So the Grassmann.jl package is so expressible, like I believe I've seen other implementations that have it like in its fully general sense like this, like for any generated algebra that you want to generate right at your fingertips. You can have this feature where like you can have these two different complex number subspaces, and then they can be like separately treated as complex numbers, but then once you suddenly make them interact with each other, they become quaternions, right? So you could be doing something like complex number stuff in this two-dimensional subspace, complex number stuff in another two-dimensional subspace, and then at some point you like combine them and multiply them or something, and then they become quaternions. And if you were using Grassmann.jl while doing that, it would just automatically upgrade you suddenly from these two-dimensional numbers that were treated separately to now these quaternions, which are unifies those, right? So this is a very powerful like way of doing it. That's with a geometric product an example. So yeah. So for example, for any vi in the grade 1 space, we define vi squared equals vi times vi, which equals gii. So that's from the metric tensor, right? So typically the diagonal metric G of the algebra is often defined by relations like this. So you could define a geometric algebra using the diagonal metric relations, for example. Then there's a null basis of the projective split. And that's basically when you have this V sub infinity and V sub empty set, and that one is like, we define like this plus or minus metric, and then we take the sum or the difference of those, and then we scale them appropriately, and then that produces a Lobachevsky plane, but with a transformed basis representation. And then the geometric product, then the metric tensor is transformed from a diagonal metric to a non-diagonal metric. And this non-diagonal metric transformation of the Lobachevsky plane produces this new geometric algebra. The geometric product behaves a little bit less intuitively. It's still the same rule, the definition that I give up here, but it behaves less intuitively than what most people understand typically in this particular case with the transformed null basis. And then we have the geometric product can be applied in two averaging operations, which are symmetrization and anti-symmetrization operations. And this is been discussed previously in some of my other, videos and papers and stuff. And we'll just keep it moving because there's a lot to discuss. So the reverse product. So consider the reverse product. So the reverse of an element times itself. So typically we think of the absolute value squared as that. And so the absolute value is the square root of this thing. And there's like a Euclidean norm of it as well. Like sometimes you want to emphasize that you want to restrict to the Euclidean case, so then you can put like a double bar if you want. But in general, the square root is like computed with this logarithm for any invertible omega, but this is the square root of like this geometric product, right? And then this is just like get you started. A simple way to calculate the algebraic inverse is the reverse of an element divided by basically this absolute value squared. And that's one way to do it. So the sandwich product is basically this operation right here, eta O/omega. So this is just my notation of it, in which case you take the involute and then the inverse and then sandwich it with eta in the middle and then omega again. But there's the alternative notation, which is the reverse definition, which is eta omega times the involute of eta inverse. And that's with these triple arrows. And this is what some other what the Clifford Python package uses. So a lot of people who use the Clifford Python package might be familiar with that convention. But I don't believe this is like a appropriate default convention. I'm not opposed to it existing, like, so you can keep using this symbol if you want. But I think there's room to define the correct convention, which is the O/ symbol, which is the opposite convention. There's basically two ways to do it. You can order the orientation. You can orient it one way or orient it the other way. And one is basically clockwise and the other is counterclockwise. And I'll get into it a little bit later again. And so now these are just some nice extra There's just some like fun little exercise regarding formulas regarding the absolute value of the real part squared and the absolute value of the imaginary part squared, and how you can think about those. And then, yeah, this is about the square root of -1. This is, some people like to, you know, wonder about the mystery of the square root of -1 and so on. And so I've just included some fun little formulas involving the square root of -1. And then I have this fun little formula right here, which is if you take the reverse of omega times omega, which is the absolute value squared, and you split omega into its real and imaginary parts, then it splits like this. It's the real part squared plus the imaginary part squared plus 2 times the real of the real times the imaginary. And this a new formula. I don't believe I've seen this as a formula somewhere else before, so this is like a cool new formula, I believe, that I came up with. So yeah. So now let's just wrap this up in a moment here and take a look at these formulas here. So we'll just take a real quick drink some water. All right, so let omega be a grade M element, then the regressive product of I with omega is omega itself. And here's a little proof of that. I've discussed this before in the past, so if you're interested in that, you can take a look at it in the paper. I'll just keep it moving. Now, if we observe that star omega equals the reverse of omega times I equals the inner product of I and omega. Since that inner product of I and omega equals I times the regressive product of star omega, and we just proved that the regressive product of I and omega equals omega, so that equals star omega. So it's just a cool little thing that I found, like, it helps me think about it. Like, I don't know, I haven't seen other people think about it like that, but this is like how I think about it. So yeah. And then we have the theorem, let omega be a grade M element, and the complement of a complement equals -1 to the m times n minus m of omega times the absolute value of I squared. Now this is called the complement of a complement theorem, and I've discussed this previously in another video on YouTube and in my paper in the past and on different occasions. And so I have a proof of how to think about it. So I've discussed this particular proof before. I've included it here as again for reference for people to familiarize themselves with some things about it. But we'll just keep it moving for now since I've discussed this before. The Euclidean complement of a complement. So the complement of a complement -1 to the m times n minus m times omega, since the absolute value of I squared equals 1. So basically the difference is that in the Euclidean case, the absolute value of I squared equals 1. So we can basically drop it, right? So that's the difference, basically, you see. So the fully general case, there's a difference between the Euclidean and the fully general case. So let omega be the grade m element. Then the inner product of omega with itself times I equals the outer product of omega times its complement. So this is a rather interesting theorem because it relates a regressive product with a complement and the exterior product with a complement of a element. So it's an interesting, result in mathematics, I think. So I provide like this proof of how to think about it here. And I believe I've discussed it before in several other videos and other places or whatever. So, and papers and whatever. So I've included it again here as well if people want to check it out. Here's some more interesting results, like the exterior product. This is a more like these get progressively more general. Like we just start out with like these simple expressions and they get progressively more general. Like this is a omega element with itself. Now we think about the more general case. What if eta and omega are not the same element? And the more progressively general it gets, the expression gets more complicated. And I have discovered what the general case is and included it here for reference if people are interested in it. And this is another simple, corollary, but just some extra information to strengthen understanding about, like the inner product of an element times I equals the reverse of it times the exterior product with its complement. And there's like these different things that are equal to each other, right? So we'll just keep it moving. And then we have this important table, the Grassmann's graded tensor right contraction is written with this greater symbol. So that's the one I discussed before. That's the right contraction, Grassmann definition. And so that shows up right here. And in terms of geometric product, it's the reverse of eta times omega, and it's the grade r minus s component, right? And then there's the left contraction, which is the opposite. And I have this full table for people who use different conventions, like the Grassmann right convention. Like some people, you can use the geometric product to figure out what your convention is. Like if using your geometric product, this is your contraction operation, then you need to use input like the reverse of eta, and then that gives you like that, because eta would have to be reversed from this between these two formulas, right? The difference between these two formulas is eta's reversed here and it's not reversed here, right? So whether eta is reversed or not, or omega is reversed or not, that's what the difference is between these in the table, right? And so that's what the difference is between these different conventions. And so this is the important one, I think. So, and then some other people might want to use these other conventions depending on what it is they want to do, right? So the common unary operations on the tensor algebra elements. So we'll just quickly, so here's a table of running through some of the operations. Like if you ask for the manifold of an element, like let's say you have 1 plus v1 2, right? If you ask for the manifold, it gives you, you know, the submanifold corresponding to that element. mdims is like the dimension of the submanifold. mdims, manifold dimension. gdims, dimension of the grade, you know, if it's a graded element. Grade returns the grade of the element. Is tensor, is it like a, is it a tensor algebra element? Is graded, is it a tensor graded element? Is it a tensor term element? You know, complement right, complement left, complement right Hodge, complement left Hodge, metric, metric extensor, cometric, involute, reverse, Clifford, conjugate, even and odd, real and imaginary, absolute value, norm, unit, normalization, scalar, vector, bivector, trivector, pseudo-scalar, value and value type. So this is just like a nice summary of some of the operations. Now, what are the binary operations, you know, like the plus and minus operation, then the wedge product and the V product, which is the exterior and regressive product. Then the right contraction and the left contraction, the geometric product and division here. Then we have this O slash, which is the sandwich, and then this triple arrow as the alternative operator orientation. And then related to tensor operators and roots of polynomials, we have the inverse. That's like the inverse of a matrix, basically. The determinant, the trace, the transpose, the compound matrix, the outer morphism, the operator of a representation of something. So we'll see how that works in a moment. But if we have like 1 plus v, 1, 2, we can get like the matrix operator representation of it. And the companion matrix of a monic polynomial, and then we have, you know, the roots of a polynomial, or the real and the complex ones, the monic roots, characteristic polynomial of a determinant of the characteristic matrix, and the eigenvalues, you know, the real and the complex, eigenvectors, and so forth. These are just utility functions. But these are all custom methods that are for the tensor operator types that are included. Some custom algorithms partially as well. So for a lot of these, well, most of, yeah. Abstract tensors and Grassmann settled on custom trigonometric identities. So the exponential, for example, can be expressed as a series like this, and the logarithm as a kind of series like this. Now, this doesn't mean that every evaluation of the exponential or whatever like gets evaluated this way, but these are just some fundamental identities that help in the most general case, like calculate when we don't have like another way of doing it or something. So this table, these custom identities have been built into the programming language as fallback cases. But if there are more special algorithms that are known later on, they could, you know, replace these some of these, you know, general rules or whatever. So let's get into interactive computational sessions. So when using Grassmann, so like we have using Grassmann here, the Cayley table can be used to recall geometric algebra information. for example, to compare the contractions or something like that. So there you go. That's like one of the KD tables right there. And that's when you want to compare like the two contractions, right? So you could compare it for you could specify your geometric algebra and get the operation, binary operation, and then get the KD table as a result of that. So one of the things that is important is the linear system of equations, and I've discussed this previously in other videos and other papers and presentations and so on. So you can solve a linear system of equation explicitly using exterior algebra. This is x equals this is the result, right? So we remark that the Grassmann methods for low-dimensional linear systems are more numerically stable than the Julia-based linear algebra methods, and they're fast. So let's do this example here. 1, 2, 3, 4, backslash 5, 6. So we ask Julia, and it's gives a decent answer. It's not exact, right? But okay. Now we try the same thing using a tensor operator. Okay. So what does this mean? It means it's exact, right? We don't have these little round off errors. All right. So that means using only exterior products, there is an explicit solution to the linear system by allocating and then calculating the exterior products and then taking the permutations with P0, right? Since the exterior products are oriented, it is sufficient to check the orientation of the hyperplanes with respect to the reference point for determining whether P0 is a point contained in the simplex. Thus, it is sufficient to check the orientation of all the same exterior products as when solving the linear systems. While calculating a linear inverse of the linear system involves only a partial application of this principle and requires also allocating the transposed dyadic result. So the point is that there's this kind of overarching narrative regarding exterior algebra and how it's used to solve linear systems, and then you can use that to check information regarding the whether a point is contained in the simplex, right? And then when you want to solve the linear inverse of a system, there's a similar calculation involved in that. This what I've described in several times before characterizes this in using the Grassmann algebra formalism. Okay. Furthermore, the this operation for solving the linear system p backslash p0, right? It is a partial application of this with the action of an operator. So consider the operator composed with inverse, right? So let's take, for example, b equals v12 plus 2v13 minus 3v23. And if you haven't done so, we need the three-dimensional basis, right? So then when you ask for the operator of be this matrix you get. Now, if you ask for the inverse of the operator, and then you ask for the operator of the inverse, okay? You see what's going on there? So we're solving the linear system on a representation of an operator, and we can either invert the operator before making it a matrix, or we can invert it after making the matrix representation, okay?